Good morning, students. Today we are going to discuss a very important chapter of biomolecules. Now, biomolecules is a very important chapter. Like most of the students neglect them because the chapter is in the last. So, till coming to the chapter of carbohydrates or biomolecule, student gets exhausted with lot of mechanism and they are not able to pay much of focus on this chapter. But this is actually a very important chapter. Every year in JEE advanced paper, there is one question definitely present on carbohydrates or proteins. Similar is the case with JEE Mains as well. So this is a very important topic. Please ensure that after the lecture, you are reading NCERT line by line, and then you are solving all the previous year papers. Okay, the previous year paper containing the carbohydrate question, especially the JEE Mains as well as advanced. Okay, so yesterday some doubts came up. I couldn't address those doubts. So let's revisit those doubts again. So there was this one question posted by some student. Basically, these were the 4 questions that went unanswered yesterday. So just have a look at the first question. Now this is a reduction reaction because we have been given dibyl H. Now we know that dibyl H is diisobutyl lithium aluminum hydride. Diisobutyl aluminum hydride. So this is a sterically hindered hydride donor. Okay. So what we have said already, that dibyl H will reduce a ester, cyanide and a acyl chloride into a aldehyde. Okay. So it will stop the reaction of ester, acyl chloride and cyanide into aldehyde and will not allow the further reduction of these molecules, because basically when we take lithium aluminum hydride, it being a strong reducing agent generally reduces the ester into alcohol, acyl chloride into alcohol and cyanide into a amine. So dibyl H basically will reduce the ester. Okay, so there are 2 groups over here. One is the ester, cyclic ester, and the other is the carboxylic acid. Dibyl H will not affect carboxylic acid, it will only reduce the ester group. So basically hydride will go and attack over here. This pi electron will shift, okay, due to which we are going to form in the first step okay. Now this O negative will push the electron and this will come out. So basically we will form a aldehyde over here. So we are going to form a aldehyde and this will be present as OH and this will be COH. Okay. So this group remains unaffected. So basically you have to remember this, dibyl H reduces ester into an aldehyde, acyl chloride into an aldehyde and a cyanide into a aldehyde. It does not affect a carboxylic group. Then the next question that came was this, okay. Basically we are heating this molecule. So I think we have to predict the product or the number of moles of CO2 evolved. Now already I have discussed that beta keto acid decarboxylates easily on heating. So basically if you look at this, this is COH, alpha, beta. So this is a beta keto acid. Similarly COH, alpha carbon, beta carbon. So this is also a beta keto acid. Similarly COH, alpha, beta. So this is also a beta keto acid, COH, alpha, beta. So this is also a beta keto acid. So if you heat it, so all of the CO2 will go out and this will be formed. Okay. Now just look at this. This is basically a 1, 2, 3. So 1,3 dicarboxylic acid. Now we know that 1,3 dicarboxylic acid on heating evolves CO2 and a monobasic acid is formed. So basically CO2 will come out from there. So we are going to form this plus a CO2 over here. Okay, so on heating this molecule, we are losing total 5 moles of CO2 and we are forming this product. Okay, so this can be a question in your integer type as well, that how many moles of CO2 is evolved. Now the third question was, basically we are taking acyl chloride and to this we are reacting R2CD. Okay, so we know that R2CD behaves like, yes, you might have guessed it right till now, it behaves like a it behaves basically like a Gilman's reagent or a dialkyl lithium cuprates. So basically what will happen, R negative would come and attack at this carbonyl carbon of acyl chloride and it would substitute Cl. So in the first step we are going to form is, there is a negative charge on this vinylic carbon. So this is going to attack and going to replace the Cl. Okay, so we are going to form this in the first step. Now the second step, we are taking aluminum isopropoxide and ethyl and isopropyl alcohol. So this is basically a reduction known as Meerwein-Pondorf reduction. So what happens over here is hydrogen is lost from here, okay, and this goes and attack at the C double bond O. Okay, so we are going to form this, and this molecule itself will change into a ketone. So this is basically MPV reduction, also known as Meerwein-Pondorf reduction. So in Meerwein-Pondorf reduction, what we do is we take a ketonic group, something like this, and we are heating it with aluminum isopropoxide in presence of a isopropyl alcohol. So this basically loses hydrogen and form a ketone, and the hydrogen goes and attack at the carbonyl group. The double bond remains unaffected. Okay. Now the next question that someone posted is what this we are having a benzonitrile. To this we are adding a Grignard reagent and doing a hydrolysis. Because in the next step we are adding NaBH4, that means we have to form ketone in this case. Okay, so we are going to form a ketone in this case, and ketone on reduction with NaBH4 will give us an alcohol. Okay, now when you treat with conc H2SO4, okay, so this has to undergo a elimination reaction. So basically we are going to form this as the product. Okay, so I hope this is clear. Okay, so these are the basic doubts that you asked, and the other doubt was heating of alpha hydroxy acids, right? Someone posted this doubt as well, that we are having this and we are heating it, right? So this is basically a heating of alpha hydroxy carboxylic acid. So I have already told you in the lecture that whenever we are having a alpha hydroxy carboxylic acid, you have to take 2 moles of it and you have to carry out a esterification type of reaction, that is 1 OH of this and COH of the other would react, water would be eliminated out and will form the structure like this. Similarly, COH of this and OH of the other molecule would react and water would be eliminated. In this case, total number of isomers formed is 3. One is optically inactive because it contains center of symmetry, and the other is optically active. Okay, so these were the 5 doubts that was asked yesterday. Okay. So now just let's start with the topic. So today we are basically going to discuss carbohydrates in detail. Okay, we will try to remember all the different structures as well as disaccharides and polysaccharides. Okay, so let's start with the lecture first. So basically, what is a carbohydrate? Okay, so if we look at the name, carbohydrate is derived from 2 words, that is carbon and hydrate. Okay, so basically this is having 2 words, carbon and hydrate. So basically earlier it was defined as carbohydrates are the hydrates of carbon. So basically they were defined as hydrates of carbon. Okay, so the general formula of it was given as CxH2OY. So this is the basic hydrate of a carbon. But this definition didn't go well because it didn't describe any structural attributes of a carbohydrate. So basically the new definition that came in was, these are the compounds having polyhydroxy aldehydic or ketonic group. So basically carbohydrates are polyhydroxy aldehydes or ketones. Okay. So basically in a carbohydrate what we are having a lot of OH group. Polyhydroxy means that it is having a lot of OH group and a main functional group as aldehyde or ketone. So this is how carbohydrates were defined, that they are polyhydroxy aldehydes or ketones. Okay. So just look at the, let's look at the structures first. So basically there was a molecule known as glyceraldehyde. Okay, so glyceraldehyde was this. Now, a very important configuration was ascribed to these molecules for better understanding and doing the nomenclature of these groups. So basically scientists came up with a new configuration which is called as capital D and capital L configuration. Now if you remember, small d configuration is basically when the compound is rotating the plane polarized light in the clockwise direction, and it is termed as dextrorotatory. Small d means dextrorotatory and it represents the clockwise movement or clockwise rotation of the plane polarized light. So basically small d is also represented by a plus sign, whereas small l or levorotatory basically means that the compound is rotating the plane polarized light in anti-clockwise manner. So it is written as small l or minus. Capital D and capital L are different. So they are basically a method of ascribing a configuration to a particular compound. Okay, so they are not related to small d and small l. Looking at capital D and capital L configuration, we cannot predict whether the compound will be dextrorotatory or levorotatory, or whether the compound will have a plus rotation or a minus rotation. Plus and minus rotation can be determined only through experiments by keeping the compound in the polarimeter and measuring its optical rotation. So capital D and L are just a configuration used to define the orientation of atoms in space. Okay, it is nowhere related to the optical rotation of the compound. So this molecule was called as glyceraldehyde. Okay. Now to determine whether the configuration is capital D or L, certain rules were given to us. So basically what we will do, now when we are doing the nomenclature of this, we know that the aldehyde is the main functional group. So the numbering of the carbon would start from aldehyde. So this would be second carbon and this would be third carbon. So we can clearly see that the second carbon is having 4 different groups, that is, it is asymmetric. So basically carbon 2 is having CHO, OH, CH2OH and H. So it is having 4 different groups. So it is basically a asymmetric center or a chiral center. So we can say that the molecule is optically active. So if you look at the asymmetric carbon, the OH is present on the, this OH is present on the right side. So we said that this is a D-glyceraldehyde. Okay. So we have already said that if the OH attached to a asymmetric carbon is on the right side, then it is called as a D configuration. And suppose if we take its mirror image, so when you take the mirror image, we will get this as the compound. Now in this compound, so this is also a glyceraldehyde, but this is the optical isomer. We can also say that this is the enantiomer of this compound. Okay. So if you look at this, this is the first carbon, this is the second carbon, this is the third carbon. The OH at the asymmetric carbon is in the left side. So that is the right side, this is the left side. So basically because it is in the left side, so it was named as a L-glyceraldehyde. Okay. So whenever a molecule of D configuration has been given to you and you have been said to write its or to draw its L form, then basically just take the mirror image. Okay. So when you are taking the mirror image, the D form would get converted into a L form. So this is also a very important question. Okay. So this is a simple way of deciding the orientation of OH. Okay. But suppose we are having a compound which is having more than say one stereo center or a asymmetric center, something like this. Okay. So suppose this is your carbon 1, this is carbon 2, this is carbon 3, this is carbon 4. Okay. So now in this case there are 2 asymmetric carbon. Okay. The one which I have numbered as 2 and the other which I have numbered as 3. So how we will assign DL configuration to this molecule? So for that it was said that observe the highest numbered asymmetric carbon. Okay. So it was said that observe the highest numbered asymmetric carbon. So this is basically one asymmetric carbon which was given number 2, and this is the another asymmetric carbon which was given a number 3. Now out of those two, number 3 is greater. So basically we have to observe the highest numbered asymmetric carbon. So because only these two are asymmetric carbon, out of these two, 3 is the higher number. So basically we have to see the carbon third. So in this case the OH is on the right side. So this was assigned as a D configuration. Okay. So questions can be asked on this also. Suppose we have been given this. Suppose we have been given this molecule. Okay. So if you look at the structure, this is 1, this is 2, this is 3, this is 4, this is 5. So in this, how many asymmetric carbons are there? If you look at the structure, carbon 2 has 4 different group attached to it, so it is asymmetric. Carbon 3 is also having 4 different group attached to it, so it is basically asymmetric. Carbon 4 is also having 4 different group attached to it, so it is also asymmetric. Now out of these 3 carbons, we have to look for that carbon which is having the higher number. So basically C4 is having the higher number, right? Fourth carbon, because out of 2, 3, 4, 4 is the highest number. So basically you have to observe the fourth carbon. Now in the fourth carbon the OH is on the right side, so basically this will also be a D configuration. Suppose we have to draw the L configuration of this, so we have to just take the mirror image of this. Okay, just place a mirror over here and draw its mirror image. Similarly, if we have to find the L configuration of this molecules, and again we have to just take a mirror image. Okay, so I hope these points are clear to you. Now suppose you have been asked to write the RS configuration of this molecule. Remember RS configuration, that is there in optical isomerism. R basically stand for rectus, which means clockwise, and S means sinister, which means anti-clockwise. So basically R and S gives us the absolute configuration of the molecule, that is the orientation of groups with respect to each other in space. Again, they are not related to optical rotation. So for determining RS configuration, there was a rule that was given by Can, Ingold and Prelog, that is also called as CIP rule. So basically in that you have to number the group according to its priority. So there will be 4 groups attached to a carbon. You have to number those groups according to their priority. Now priority was based on, simply it was based on atomic number. Okay, so if you look at this, there is a carbon over here, there is a oxygen over here, there is a carbon over here, there is a hydrogen over here. We know that the oxygen is having a higher atomic number, so this will be given number 1. Similarly, these two are having carbon, so they again have the same priority at this case. But whenever the first atom is same, what we have said, we have to see the upcoming atoms. So because there is a double bond oxygen over here, so we have to convert it into a single bond. So basically this will have the second priority and this will have the third priority, and hydrogen will have the fourth priority. Now remember the rule, we have already said that the least priority atom, in this case the least priority atom is hydrogen, so it should be away from the viewer. Now if you look at fourth, because it is on the horizontal line, it means that hydrogen is coming outside the plane. Okay, so fourth, that is the least priority group, should be inside the plane, okay, or should be away from the viewer. But this horizontal line on a Fisher projection indicates that the atom are coming outside the plane. So basically you have to just neglect the fourth group. Okay, you have to just see how we are approaching 1, 2 and 3. So basically we are approaching 1, 2 and 3 in a anti-clockwise manner. So because it is anti-clockwise, it should be a S configuration, but because the least priority atom is not inside the plane, okay, since the least priority atom is not inside the plane, so it will be basically a R configuration. Okay, so this basically D-glyceraldehyde is also the R form. Okay, so let me take more example for clear understanding of this. Suppose we are having something like this. Suppose we are having something like this. Okay, now suppose we have been said to assign RS configuration. So we know that this is a asymmetric carbon. So this has 4 different group attached to it, one being COH, Br, CH3 and the last being hydrogen. So we have to prioritize these group according to their atomic number. So Br is having the highest atomic number, so it is given priority 1. After that there is a carbon, there is again a carbon, so both of them are having same atomic number. So we have to see the atoms attached ahead. So there are oxygen over here and there is only hydrogen over here. Oxygen has higher priority because it is having higher atomic number than hydrogen. So this is your priority 2 atom and this is your priority 3 atom, and the hydrogen which is having least atomic number is the least priority atom. So what I have said, we have to just forget the least priority atom, okay, just we have to see how we are moving from 1, 2 and 3. If it is clockwise, then it becomes a R configuration. If it is anti-clockwise, it becomes a S configuration. Now the least priority atom should be inside the plane. Okay, least priority atom should be inside the plane or away from the viewer. Now because in a Fisher projection, vertical line represents that the atoms are going inside the plane. So basically the least priority atom is present inside the plane. So just forget this. So just look at this 1, 2 and 3. So while tracing 1, 2 and 3, we are basically going in a anti-clockwise manner. So this represents a S configuration. Okay, so I hope this is clear to everyone. So basically we have said that the glyceraldehyde also represents the R form. Okay, so suppose a structure like this has been given to us, and suppose we have been said to assign RS configuration. Okay, so there are 2 or 3 methods available over here. Either we can do the rotation of the groups and decide the DL configuration, or we generally look at the RS configuration. Okay, so let us give the carbon chain the number. Okay, so basically it will start from aldehyde because of the functional group, 2nd, 3rd, 4th and 5th carbon. Okay, so basically we are having 3 asymmetric carbon, 2, 3 and 4 as they are attached to 4 different group. So basically we have to look for the highest numbered asymmetric carbon, that is 4. Now OH is not present over here, this CH2OH, OH is present over here. So we cannot directly comment about D or L, but we know that a D molecule is having a R configuration and a L configuration would have S configuration. Okay, so basically we have to find the RS configuration of this carbon. So we will say that this is the priority group because it is having oxygen. This is carbon over here, it's carbon, it's hydrogen. So oxygen is having higher atomic number. The second priority would be of this group because it is having more atoms with higher atomic number. Then the third group would be CH2OH and fourth group would be hydrogen. So the least priority atom again is here is hydrogen. Now hydrogen is present on the horizontal line. Horizontal line means atoms coming outside the plane. So for determining the RS configuration, the atom has to be inside the plane. So in that case, whenever there is a least priority group coming outside the plane, we will just neglect that least priority group and we will see the rotation between 1, 2 and 3. Okay, whatever configuration we are getting, we will write the opposite of it because the least priority group was not inside the plane. If the least priority group is inside the plane, we will neglect the group and we will see, we will trace the path of 1, 2 and 3. If it is clockwise, then it is R. If it is anti-clockwise, then it means it is S. But if it is outside, then we will just neglect the least priority group. Whatever configuration is coming, we will write opposite to that of configuration. So just we will neglect the least priority group. Okay, so if you look at 1, 2 and 3, so basically for 1, 2 and 3, we are tracing a clockwise path. Now because this is outside the plane, so it would be a S configuration. Now we know that a S configuration represents L form. Okay, so this is basically a L form. Okay, so I hope this is clear to everyone. Okay, so basically we assign DL configuration to the sugars. Okay, so suppose we are having a sugar something like this. Now how we will call this molecule? Now if you look at this, this is basically having 1, 2, 3, 4 carbon. Okay, and it is basically having an aldehydic group. So this is also called as, suppose there is one more OH over here. So if you look at this, this is 1, 2, 3, 4, 5. So basically it is having 5 carbon and an aldehyde group. So the name of this is, general name is aldopentose. Okay, so the name of the sugar always end with OSE. Like if you look at glucose, it is ending with OSE, sucrose, OSE, maltose, OSE, lactose, OSE, fructose, OSE. Okay, so most of the monosaccharides, oligosaccharide name ends with OSE. So the name would end with OSE because there are 5 carbons, so we'll call this as pentose. There is an aldehyde group, so we'll call it as a aldopentose. Suppose we are having this as the structure. So in this we can clearly say that there are 1, 2, 3, 4, 5 carbons, okay, and there is a keto group present over there. So because there are 5 carbons, so we'll call this as pentose. Pentose means 5 carbon sugar, and we are having a ketone group, so we'll call this as ketopentose. Okay, so we basically, when we are having 6 carbon, we'll say it is a hexose. If an aldehyde group is present, we'll call it as aldohexose. If a keto group is present, we'll call it as a ketohexose. Okay, so these are the very basic that you should know. Okay, so if we want to prepare, now this aldose family chart is important. There are many other ways to remember them also. I will get to it. So basically, if we want to prepare sugars or carbohydrate, we prepare it through a reaction which is known as Fischer-Killiani synthesis. Okay, so this is basically Fischer-Killiani synthesis. Okay, so in a Fischer-Killiani synthesis, I will just show you what are the steps involved and how do we get the sugars of the next family. So suppose you are taking a glyceraldehyde. Okay, suppose we are starting with D-glyceraldehyde and we are adding HCN. Okay, now the best part of carbohydrates, which I feel, is the application of aldehydes and ketones and alcohols in this chapter. So basically these are very simple chapters, only the structure becomes big, but at the core of it, if you look properly, that is basically involving a aldehyde ketone reaction or a alcohol reaction. So you need to be thorough with your basic aldehydes and ketones and alcohols, then only this chapter becomes interesting. Okay, now because we are adding HCN, we know that addition of HCN on aldehydes or ketones form a cyanohydrin. So basically this carbonyl carbon will be protonated and CN negative will attack. Now because this is a sp2 carbon, okay, because if you write the structure in an open manner, so if you write the structure something like this, so basically this is a sp2 hybridized carbon, so this is planar. So basically CN negative can attack from the front side or the back side. So there are two cases possible when HCN attacks on this. The first case would be, we would form, like whenever HCN adds, we form cyanohydrin, that is a OH and a CN get attached to the carbonyl carbon. So basically we will get this species. Okay, so basically CN negative is attacking and OH of this carbon is coming on the right side, or this CN negative is attacking and OH is going on the left side because it is planar in nature. So there will always be two configurations that will be formed during the course of this reaction. So basically we are going to form these two compounds, okay, because it's a very simple reaction, something like this. We are having an aldehyde and to this we are adding HCN or KCN. Okay, so we are going to form RCOH HCN. Because this carbon is having 4 different groups, it is optically active. So basically the two isomers will be formed, one in which OH is suppose in the plane above or outside the board, and one in which OH is going inside the plane. So basically there are two orientation possible because this was a prochiral carbon. Okay, prochiral carbon is the carbon which on attacking by a species gets converted into a chiral carbon. So because of this there will be two isomers that will be formed, one in which OH is on the right side and the other in which OH is on the left side. Now in second step, suppose after addition of HCN we do a hydrolysis. Now we know that on hydrolysis CN will convert into a COH Okay, so CN basically gets converted into COH. Okay. So what happens after this is there is a basically intramolecular esterification type of reaction that is taking place. So what happens, this OH and H is removed. So basically this is your first carbon, second carbon, third carbon, fourth carbon. So this OH and this H gets removed in the form of water. So basically we form a species something like this. Okay, so this gets joined through this. Let me release this. Okay, so this gets joined through this. Okay, similarly, this gets joined to this. Okay, so first we are forming cyanohydrin, which on hydrolysis was giving a COH. Then it was forming a intramolecular ester. So basically, these pointed ends are not carbon. Just remember that. This is just that we are showing that a cyclic ring will be formed between first and the third carbon. Okay. So in the last step, what we do is we treat them with sodium amalgam. So this basically reduces this ester into a aldehyde group. So we get CHO, OH, OH, CH2OH, H, H, CHO. Okay, so this is OH is on the left side, OH, CH2OH, H and H. Okay, so I hope this is clear to everyone. Now this is again a D configuration. The highest asymmetric carbon has the OH on the right side. This is also the D form because the highest asymmetric carbon has OH on the right side. Okay, so this is known as Killiani-Fischer synthesis. Okay, what has happened in this? If you look at this, we started with a D-glyceraldehyde molecule. We treated it with this reagent. What happened? There was just an addition of carbon over here. So this is basically a step-up reaction. If you look at this, this was the, if you just remove this, this was the initial structure which we started with, which was glyceraldehyde. So this, if you remove this, this was the initial structure which we started with, which was glyceraldehyde. So upon reaction of this molecule in a Fischer-Killiani synthesis, there is the introduction of one carbon, okay, between CHO and this carbon. So basically that carbon will have OH either on the right side or on the left side. So two isomer will be formed. Now this is called as erythritose. Now how to remember? This is called as threose. Okay, one way of remembering this is when you do a glyceraldehyde Fischer-Killiani synthesis, for the first time you get erythritose and threose. Now if you look at this erythritose, there are 3 bars, okay, and all of them are towards one side. So basically these bars are all on the one side. Similarly, if you look at the structure, all the OH are on the one side. So that is why it is called as erythritose. If you look at threose, if you look at this, there is 1 bar over here and 1 bar over here, then it will form a T. Okay, so basically the two groups are opposite. So OH and OH are opposite. So this is basically erythritose and that is basically a threose. So this is how you do the Fischer-Killiani synthesis. Okay, so I hope this is clear to everyone. So if you look at this, the aldose family, so we are starting with a D-glyceraldehyde. We are doing a Fischer-Killiani synthesis. So basically in a Fischer-Killiani synthesis, I have already told you, we'll insert a carbon between CHO and this group. So basically we have marked this group. So the insertion would take place between this group. So this there a carbon would come. The OH can be on the right side. The OH can be on the left side. So basically we are forming D-erythritose and D-threose. Okay, so this is having, if you look at this, this was having a plus optical rotation, but these are having minus optical rotation. Okay, so they are basically determined experimentally. We cannot just say about plus or minus looking at their D or L configuration. Okay, so when you do a Fischer-Killiani synthesis of this molecule as well, there would be introduction of another carbon over here. So another carbon came over here. The OH will be on the right or on the left side. This is called as D-ribose. Okay, again a very important molecule. This is important. You should know the structure because this is used in DNA and RNA structures. Similarly, when you get this on the left side, it is called as arabinose. This is also important. Okay, when you treat threose in a Fischer-Killiani synthesis, a carbon will be introduced, OH on the right side first, OH on the left side. This is called as xylose, this is called as lysose. Okay, now if you do the Fischer-Killiani synthesis of ribose, again a carbon would be introduced, OH can be on the right side as well as on the left side. On the right side it is called as allose, on the left side it is called as altrose. Okay. For arabinos, if you do a Fischer-Crillon synthesis, a carbon will be introduced over here. So we will get a, if it is on the OH is on the right side, we will call it as a glucose. If it is on the left side, we will call it as a mannose. Similarly, if you take xylose, do Fischer-Crillon synthesis of this, we will get OH either on the right side called as gulose or on the left side getting iodose. Similarly, if you do for lysose, we will form galactose and talose. Okay. Now, do you have to remember all these structures? Definitely no. But if you can remember these through Fischer-Crillon synthesis, it will be little easy. Okay. Another way to remember is remembering the epimers. Now, what are epimers? Epimers are diastereomers. So, basically this is a diastereomer that differs in configuration. Okay, so this is basically a diastereomers that differs in configuration at one of the carbon. Okay, so basically the stereochemistry about all the carbon will remain same. The stereochemistry about only one carbon will change. Okay, so let us look at the structure of glucose. So basically this is having 6 carbon. Okay, so if we look at it closely, the second OH is on the right side. If you look at the mannose, second OH is on the left side. Third OH is on the left side, third OH is on the left side, fourth OH is on the right side, fourth OH is on the right side, fifth OH is on the right side, fifth OH is on the right side. So basically in these two molecules, there is a difference in configuration at about only one carbon. So such compounds are called as epimers. Okay, so epimers are basically diastereomers that differ in configuration at about one carbon only. So I will say that if I take glucose, okay, the C2 epimer of glucose is a mannose. Okay, so you know the structure of glucose, just draw the C2 epimer. C2 epimer means you have to just change the orientation of OH from right side to the left side, you will get mannose. Similarly, if you draw the C3 epimer of this, so basically C3 epimer would be, this is 1, 2, 3, so just put the OH on the right side. So if you look at the structure, we will get allose. So basically the C3 epimer of glucose is a allose. C2 epimer is mannose, C3 epimer is galose. Similarly, draw the C4 epimer. So while drawing the epimer, what we have to do? We have to retain the stereochemistry at all the carbon, only the stereochemistry at fourth carbon will change. So if you look at this is 1, 2, 3, 4, 5, 6. So because it is a C4 epimer, so what we'll do? We'll put the OH from the right side to the left side. So if you look at the structure, we'll get the structure of galactose. Okay. So just remember this. This is actually easy to remember, and that direct question can come on this as well. Okay. So glucose C2 epimer is mannose. Glucose C2 epimer is mannose. Glucose C3 epimer is allose. Glucose C4 epimer is galactose. Okay. Similarly, if you look at ribose and arabinose, okay, ribose and arabinose, this is 1 carbon, 2, 3, 4, 5, 1, 2, 3, 4, 5. First OH on the OH, first OH on the left side. Okay, so basically they are C2 epimer. Okay, so you have to remember the epimers. You can remember the epimer like this. Glucose epimers are important. Ribose, arabinose are important because from arabinose we derive glucose and mannose. So arabinose is actually important. So glyceraldehyde changing into erythriose and threose. Okay, and erythriose then giving us arabinose, arabinose giving us glucose and mannose. Okay, so I hope this is clear to everyone. Okay, so another way of synthesizing is the rough degradation. Okay, so rough degradation is basically a step down reaction. Fischer-Crillon was a step up reaction. We were increasing the number of carbon. Rough degradation is basically a step down reaction. We are decreasing the number of carbon. So basically, let us take any carbohydrate. Okay, so if you can see, this is basically erythriose. Okay, to this we add bromine water. So bromine water is an oxidizing agent. It will oxidize CHO into COH, and in the next step we added iron 3 plus and H2O2. So what would happen? A CO2 molecule would go out. Okay, so this will go out and this will oxidize into a aldehyde. So basically we are losing one carbon, we are forming diglyceraldehyde. Okay, so we wanted to form erythriose from diglyceraldehyde, we had to carry out a Fischer-Killiani synthesis because this was a step-up reaction. Okay. So now let's quickly come to the reaction of glucose. So if you look at the structure of glucose, the structure of glucose is something like this. Okay. So there is a CHO. Okay. The first OH on the right side, second OH on the left side, third OH on the right side. Okay. So remember like this only, if you are having difficulty in remembering the structure of glucose, so you have to just remember that glucose is a 6 carbon. So this is basically a hexose because it is having an aldehyde group, so it is a aldohexose. Okay. So basically write a CHO first, then the second carbon OH on the right, third carbon OH on the left, fourth carbon OH on the right. Now because this is a D form, so the fifth carbon OH will be on the right side. Okay. So in all the cases, because I have already told you these are the different D aldose family, so in all the cases the last carbon is having OH on the right side. Okay. So just remember that the last carbon will have the OH on the right side. Okay. And then CH2H. So this is the basic structure of glucose. If you want to draw its L, just do a mirror image of this, you will get L-glucose. Okay. So if we look at the reaction of glucose, so there are few reactions that you should know over here. So when you are taking, just see how I am drawing. CHO, first carbon OH on the right side, second OH on the left side, third OH on the right side. Okay. So first, second, third, fourth. Okay. Fifth carbon always has the OH on the right side because they all belong to D family. Okay. So if we treat this with HI, okay, so just remember we have already done this in alkane. HI basically reduces alcohol into alkanes as well as carbonyl compounds into alkanes. So this will reduce this into CH3, CH2, 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 CH3. So we are going to get N-hexane. So if you heat with phosphorus HI, you are going to get, or simply HI, you are going to get N-hexane. So this reaction proves that the glucose is having a linear structure. Okay. So the groups are arranged linearly. That's why we are getting a hexane and not a substituted hydrocarbon. The second important reaction is if you add bromine water to this. Okay. So bromine will basically oxidize CHO into COH. So the remaining skeleton remains same. First OH right, second OH left, third OH right, and fourth OH is always on the right. So this is called as gluconic acid. Okay. Now if you react this with HNO3, HNO3 is a strong oxidizing agent. So it will basically oxidize the primary alcohol as well as the aldehyde. So we are going to get, okay, the skeleton would remain the same and both would convert into COH, sorry. So basically we are getting saccaric acid in this case. So basically on treatment with HNO3, they convert into alderic acid. Okay, alderic acid is a general term. With glucose, we will say that it has converted into a saccaric acid. So these are basically your NCERT reactions. Okay. Now if you react this with say acyl chloride. Okay. Now remember this was again a reaction of alcohols. We have already did this acylation of alcohols. So whenever we wanted to find the number of alcohols present in a given compound, so we are treating that alcohol with acyl chloride. Okay. And there was an increase in molecular weight of 42. Okay. So this is basically having 5 OH groups. So this will consume 5 CH3COCl or 5 moles of anhydride. Okay. So I am just going to write this. So we are going to form, this will change into OAC, this will also change into OAC, so this will also change into OAC, this will also change into OAC, and this will change into OAC. So basically in this there were 5 acyl, there were 5 OH group, so they all would react with acyl chloride and change into a OC double bond OCH3 group. So the increase in molar weight would be by 210 units. Okay. So I think you remember all these reactions. These are the very basic reactions that are also given in NCERT and are very important. This reaction has been asked in the JEE Mains paper. This reaction has been asked in the JEE Mains paper. This reaction has also been asked in the BITSAT paper. This reaction is asked on the BITSAT paper. Okay, and this was also asked in the previous year IIT. Okay, so D-glucose is given to us, just write the L-glucose. So remember these reactions, these are important reaction. So basically this reaction confirms that there are number of OH group is 5 because it is consuming 5 mole. This reaction confirms the presence of a aldehyde group. This reaction confirms us the presence of a 1 degree alcohol because it is getting oxidized into acid. Okay. Now one more important reaction would be if you treat this with, okay, so this is the basic skeleton. If you treat with this NH2OH, hydroxylamine, so this also reacts with the aldehyde group and form oxime. So this confirms the presence of, okay, so we will form a skeleton something like this. Okay, so this will confirm the presence of aldehyde group and forms oxime. Okay, similarly, if you react this with HCN, so this will form a cyanohydrin. So again it will confirm the presence of a aldehyde group. Okay, I am not writing the OH every time, so it is assumed that this is the skeleton of glucose. Okay, so these reaction basically confirms the presence of aldehyde. Bromine water addition also confirms the presence of aldehyde. When you add bromine water, only aldehydes are oxidized, so it basically confirms aldehyde group. When you add HNO3, it oxidizes both aldehyde and a primary alcohol, so it confirms a primary alcohol. With acyl chloride we confirm that there are 5 OH group. Okay, but if you look at the glucose, there are some reactions beside glucose having a aldehyde group, it does not give few reactions of aldehyde. So basically if you look at the few important reactions that has been taken from NCERT again, so because despite having the aldehyde group, glucose does not give Schiff's test. Now we know that aldehyde generally gives Schiff's test, they restore pink color of Schiff's, but aldehydes, glucose does not give this test, and it does not form hydrogen sulfide addition product with NaHSO3. So this is again a very important context you should know over here. Directly they can ask in the paper which of the following statements confirm the presence of a cyclic structure. Now because CHO group was there, so it should have given the Schiff's test, but it is not giving. Because CHO group was there, we have already studied in aldehyde ketone, it should give a addition compound with sodium hydrogen sulfide, but it didn't give. It means that the CHO present in the open chain structure was not present. Okay, somehow it was cyclizing in the molecule. The pentaacetate of glucose does not give hydroxylamine test, indicating the absence of free CHO group. Okay, so basically what it was assigned from here that glucose is having a cyclic structure. So just see how we are writing the structure of glucose in a cyclic manner. Okay, and then I will tell you the shortcut to remember them. Now we have already done that. Aldehydes or ketone react with alcohols and form hemiacetal or acetal group. So there are so many OH group over here and there is a CHO group over there. So basically it will undergo a nucleophilic addition reaction. A OH will attack on CHO and form a hemiacetal, okay, ring. So for writing the hemiacetal ring or drawing the cyclic structure, I will just take this structure, rotate this structure by 90 degree. So when I rotate this with 90 degree, okay, I will just rotate this by 90 degree in a clockwise fashion. So basically I am going to write CHO over here. Okay, this is just for my convenience so that I am able to draw the cyclic structure easily. So basically I am taking this molecule, I am rotating it with 90 degree. So when I rotate this with 90 degree, this is the first carbon, this is the second carbon, this is third, this is fourth, this is fifth, this is sixth. Okay, so when I rotate this by 90 degree, the OH group which was lying on the right side at the C2 carbon, if I rotate it with 90 degree, this will completely go in downwards. Okay, so it is just like this. If I rotate this, okay, the OH on the right side will go, like will point in the down direction. Okay, so basically the second OH will go in the will go downwards. Now the third OH and the relationship between the second and the third is, third, which if I rotate with 90, third will come, okay, will go above, okay. Similarly, if you look at the fourth, fourth will also come down, okay. So just if you are able to do for one, suppose second OH, if I can see that it is going in the downward direction, so the third OH is opposite to it, so third is opposite to it, okay. Fourth is opposite to that of third, and fifth is, okay, so this is third, this is fourth, this is fifth, this is sixth. Fourth and fifth has the OH in the same orientation, same direction, so OH will be in the same direction. This is downward, so this is also downward, okay. So when you rotate this, okay, so we will get H over here and CH2OH over here, okay. So I hope this is clear to everyone. So just you have to like take this structure and rotate it 90 degree clockwise, so that CHO comes over here, the OH will go down, okay, and rest OH you can take the orientation with respect to each other, okay. Or you can also do it by seeing that when you are rotating the third OH, the OH on the left side will come above, the OH on the right side will always point downwards. So this can basically, lone pair can attack on this carbon, but in that case it will be forming a 7-membered ring. So what happens is, we generally do the rotation of all the groups, okay. So when we rotate all the groups clockwise, so their orientation in the space won't change. So basically we will get a structure something like this, okay. So the OH will come over here, CH2OH will go above, okay. This OH is pointing towards downward, the OH is pointing upward, and this OH is pointing downwards, okay. Now this oxygen lone pair can attack at this carbonyl carbon, and this pi electron get polarized. Now because this is sp2 hybridized carbon, so when oxygen attacks over here, so the OH can go either like inside the plane, which we can write pointing downwards, or it can go outside the plane pointing upwards, because this is a sp2 carbon, okay. So what we get over here is a structure something like this, okay. So suppose it attacks at this carbon becomes optically active, so two forms can be drawn, OH going inside the plane, or we are showing it downwards, okay. So this is one form, or the OH going outside the plane, or okay, above. So this is the form, okay. So these are the two forms of glucose in cyclic structure, okay. So basically if you look at this, this is the first carbon which we started with, this is also the first carbon which we started with, this is the second, this is third, this is fourth, this is fifth, this is sixth, this is 1, this is 2, this is 3, this is 4, this is 5, this is 6, okay. So basically this is the cyclic structure of glucose. So there are two cyclic structure of glucose possible. Now because it has formed a 6-membered ring, 6-membered ring with the oxygen is generally known as a pyran. Because it is a sugar, we will call it as a pyranose. So basically this is a pyranose, okay. So we will call this as a pyranose, okay. Because it is formed from a glucose, we will call this as a glucopyranose, okay. Now if you look at the first carbon, this is the hemiacetal carbon because it is attached to a OH and a OR group. Similarly this first carbon is your hemiacetal carbon, okay. So this is also attached to OH and a OR group. Now if you look at these two structure, they basically differ in configuration at the carbon number 1, okay. So the orientation of OH at all the other carbons are same, the configuration of carbon are same, only the configuration varies at the first carbon, okay. So such relation between compounds are called as anomers, okay. So basically anomers are special kind of epimers. Epimers was the configuration about all the carbons are same, it will differ at only one carbon. Okay, so these are like epimer only, but there is a difference between epimer and anomer. In basically anomers, there is a difference in configuration at a hemiacetal carbon, and in epimer it can be at any position. Okay, so basically anomers are diastereomers that differ in configuration at a hemiacetal carbon, so they are called as anomers. Now one of them is a alpha form and the other is a beta form. Okay, so this is basically a alpha because it is derived from the D form, so we will write this as alpha D glucopyranose, and this is a beta form, so this is beta D glucopyranose. Okay, now how we define this alpha beta form? Look at the OH at the first carbon. This OH at the first carbon and the OH at the sixth carbon, they are in the same plane. Okay, so they are basically in the same plane. So whenever they are in same plane, we will call this as a beta form, and in this case the OH at the first at the sixth carbon, they are opposite to each other. So basically they are opposite, so that's why they are termed as beta form. Okay, so I hope this structure is clear to everyone. Also you can draw its structure in the chair form. Okay, if you look at the chair form, when you put all the OH in the equatorial position, okay, we are putting all the OH in the equatorial position, so this is your beta form. Okay, and if you put the hemiacetal, like this is the OH, this is the first carbon, so this is the first carbon, so basically they are anomers. So because if one is down, other is upwards, so basically you have to differ the configuration at that particular carbon. So if you draw this, it becomes a alpha form. So basically in beta all the OH are in the equatorial position, and in alpha the hemiacetal carbon OH is axial. Okay, so if you look at this first carbon OH and the sixth carbon OH, they are in the same plane, so there is called as a beta form and the other is called as a alpha form. We can clearly say that beta form is more stable than alpha form because all the bonds are in equatorial position. Okay, so beta is the dominant form. Okay, so I hope this is clear to everyone. Okay, so this is the basic cyclic structure. So basically if you are drawing the cyclic structure, just draw something like this, draw a ring containing oxygen. Okay, the first, leave this one because this is the anomeric carbon. Okay, so the first, the carbon at the OH, just place it in the downward direction. Okay, other at the upward, then the next carbon again downward, then the next carbon contains CH2OH in the upward. Okay, so you can draw this skeleton, OH down, OH up, OH down, OH, CH2OH up. Now this carbon can have OH in the upward direction, so this will become your beta form. Okay, so this basically becomes your beta form. If it is down, then it becomes a alpha form. Okay, so basically if you keep them in solution, these will change into these rings. So basically we say that they undergo mutarotation. Okay, if you keep the acyclic form in the aqueous solution, it will cyclize into alpha form and the beta form, and there will be a equilibrium established, due to which the optical rotation of the compound will keep on changing, and this is called as mutarotation. Okay, so this is called as mutarotation. If you look at this, glucose is found to exist in two different crystalline forms which are named as alpha and beta. The alpha form is having melting point of 419, is obtained by crystallization from concentrated solution of glucose at 303, while the beta form is having 423 Kelvin. Okay, so basically you have to remember the melting point as well. The question can be asked on the melting point data also, so that is there in the NCERT. Okay, so beta form is having more, beta form is more stable, beta form is having more melting point, so that is the way you remember. Okay, so if you look at the cyclic structure of fructose, now fructose is basically a keto hexose. Okay, so you have to draw, now when we are drawing the structure of glucose, okay, we are saying that there was a CHO, then OH on the right side, first OH on the right side, second OH on the left side. So basically you are just doing a tautomerism at the first and second position. We are taking the hydrogen from, okay, the alcohol and putting it on the aldehyde. So basically this was the structure of glucose, okay. Remember the way I told you, first OH right, second OH left, third OH right. This will always be on the right side because they belong to D family, okay. So what we are doing, we are just putting this hydrogen at the carbonyl group, aldehyde group, and we are forming a ketone over here. So basically it is undergoing tautomerism, okay. The remaining carbon will have the same stereochemistry. So this OH will be on the left side, this OH will be on the right side, and this will always on the right side. So this is basically the structure of D-fructose, okay. This is having optical rotation in the anti-clockwise manner, hence it is written as dextro-rotatory. D-glucose always rotates the light in the, okay, in the clockwise manner. So this is basically having a rotation of 52.7 degree, and this is something like minus 92 degree, okay. So when you draw the cyclic structure, you just attack a OH from here to C double bond O, so you'll get a 5-membered ring, okay. So that is called as fructofuranose, because 5-membered ring containing oxygen is called as furan, okay. So this internally attacks in the same manner, just rotate it in the 90 degree, okay, bring C double bond over here and attack the OH group to form a 5-membered ring. So basically it will form a fructofuranose, okay. So when the first CH2OH and 6 CH2OH are in the same plane, it is called as a alpha form, okay. And when, if you look at the, when the first OH, the carbon at the hemiacetal OH, okay, the OH at the hemiacetal carbon, okay. So this is the hemiacetal carbon over here, so I will just erase it. So basically if you look at this form, we will form a hemiacetal carbon over here. So the OH at the hemiacetal carbon and the 6th OH group, they are opposite, so this is basically a alpha form. Similarly, if you look at this, the OH at the hemiacetal carbon, okay, and the 6, they are in the same plane, so this is basically beta D-fructofuranose. So basically they are anomers, okay. I hope you can draw these structures, okay. So if not, you can directly remember these structures. So basically it is a 5-membered ring, okay. Just leave this position because this is a hemiacetal. OH can be above, OH can be below. Third OH is always on the right, okay. Fourth OH is opposite, then the 6th CH2OH is opposite. So if this OH is over here, CH2OH over here, so this is basically beta form. If you write the opposite, it is a alpha form, okay. Now let us consider a glycosidic linkage. Now basically we say that we are dealing with monosaccharides. Monosaccharides are basically a single unit which on hydrolysis does not give any other carbohydrates, okay. So examples are glucose, fructose, okay. These are the few examples. Even galactose, galactose, altrose, allose, they are all monosaccharides. So they do not hydrolyze to give any further unit. If you consider disaccharides, so basically disaccharides would be disaccharides, oligosaccharides, or any polysaccharides on hydrolysis gives n number of or gives more units of monosaccharides. Suppose if you take a disaccharide, you hydrolyze that, you will get 2 units of monosaccharide. If you take a trisaccharide, okay, and hydrolyze it, we will get 3 monosaccharide. If you hydrolyze a polysaccharide, we will get n numbers of monosaccharides. So basically in disaccharides, oligosaccharides or polysaccharides, the carbohydrates or the monosaccharides are connected to each other. So they are connected through a glycosidic linkage, okay. So basically glycosidic linkage is a ether type of linkage that connects. So glycosidic linkage is the ether type of linkage that connects to monosaccharide, okay. So if you look at, say, let us take an example of this monosaccharide, okay. So this is basically your second carbon, this is the first carbon, so this is basically your hemiacetal carbon. And let us take another example, take this only. So this is again a hemiacetal carbon, okay. So basically it can get joined. So this is one monosaccharide, this is another monosaccharide. So the two monosaccharide can be joined through these condensation of these OH. So basically when you condense these OH, so what we get is we have to just remove water from them. So I have to write this structure in this manner. Okay. So basically what I have to do, I have to just remove water. So when I remove water from them, H and OH from them, so we basically get this. So we are forming, this is called as a glycosidic linkage. This is the linkage between two monosaccharides. It is the ether type of linkage. Okay. So this is basically a glycosidic linkage between the first carbon of the two monosaccharides. Okay. So we'll say that this is 1,1 type of glycosidic linkage. Similarly, if we take 1 and 4th carbon of this, okay, 4th carbon of the other monosaccharide, and we remove water, so in that case we will be getting okay this as the structure. So this is basically 4th carbon and this is the first carbon. So this would be basically a 1,4 glycosidic linkage. Okay, I hope you understand these terminology now. So basically glycosidic linkage is the ether type of linkage that joins two monosaccharide. Okay, we can join the two monosaccharides either through their hemiacetal carbon. In this case, this is the hemiacetal carbon 1, numbered 1. This is also the hemiacetal carbon numbered as 1. So basically when you join that, we'll get a, remove water, we'll get a glycosidic linkage. So this glycosidic linkage is formed between the two hemiacetal carbon of the monosaccharides. And in this case, the 4th carbon of one monosaccharide and the first carbon, that is the hemiacetal carbon, is forming the bond, and we'll remove water and we'll form this. Okay. Now we can also name these glycosidic linkage. Now this bond which was forming the glycosidic linkage. Okay. So if you look at this bond, this is a hemiacetal carbon. Okay. So this was basically the first carbon OH was going down and this was going upward. So basically they are in the opposite plane. So whenever they are in opposite plane, we'll call this as a alpha bond. Okay. So this is basically alpha form of the glucose. Okay. And if you look at this is also the alpha form because OH and the first carbon OH and the 6th OH is in the opposite plane. So when you are forming this linkage, 1,1 linkage, so I can call this linkage as a glucosidic linkage. Okay, I am just adding SIDIC word, meaning it is a glycosidic linkage. So this is basically glucosidic because glucose is forming. Okay, so this is glucosidic. Now this bond was in alpha orientation, so we can call this as a alpha glucosidic linkage. Okay, similarly if you look at this bond, okay, this was also alpha with respect to this ring. So this is also a alpha glucosidic linkage. Okay, so these are very important questions comes on their linkage nomenclature. Okay, now if you look at this structure, okay, now this carbon was a hemiacetal carbon which is forming a glycosidic linkage. So basically if you look at this carbon, this was the alpha form because the OH and the 6th carbon OH was in the opposite plane. So basically this is alpha glucosidic. But if you look at this bond, can we call this as a alpha or a beta bond? We cannot call it because this is not the hemiacetal carbon. So alpha beta nomenclature is always done when the OH group is attached to the anomeric carbon or the hemiacetal carbon. Okay. So in this case, this was your alpha bond. So this does not have any name. So basically we will say that this is having only alpha glucosidic. It is said that it is having alpha glucosidic. That means both hemiacetal carbon must not have been joined together. When we are saying this is alpha with respect to both the rings, okay, that means they are joined through the hemiacetal or the anomeric carbon. Okay, so this is a very important point. Okay. So basically after this comes is reducing and non-reducing sugar. All the sugar that gives Tollens reagent test, okay, that gives Tollens reagent test or Fehling solution test, okay, all those sugar which gives Tollens test, Fehling solution test and Benedict test are called as reducing sugar. Okay. So basically if I talk about a sugar, cyclic structure. So we know that, say this is having a hemiacetal linkage, this carbon is attached to OH and OR. So we know that from the idea of aldehydes and ketone that hemiacetal bonds are unstable, so they will basically open up. Now when they open up, okay, so they will basically, we'll get a free aldehydic group. Now because this has a free aldehydic group, so this will be called as a reducing sugar, as the aldehyde will give test with Fehling-Tollens or Bendix solution. Okay. Now alpha D-glucose or a beta D-glucose, because they have a, okay, because they have this hemiacetal carbon, so they will open up giving the free aldehyde, so they are basically reducing sugar. Similarly fructose form a 5-membered ring, okay, fructose form a 5-membered ring, it can also open up because it was a it has a hemiacetal carbon, so basically fructose is also a reducing sugar. Or you can look at the structure of fructose. Okay, I already said that the structure of fructose, this is basically a alpha hydroxy ketone. Okay, so people remember like this also. We know that and aldehyde gives a Tollens agent test, and a alpha hydroxy ketone also gives a Tollens agent test. So because this is alpha hydroxy, so this will also give the test of Tollens reagent, Fehling solution and Benedict solution. Okay, or you can look by the cyclic structure. Now suppose we are having these two sugars. Just look at this. This is the main question that is formed in this case. Okay, suppose we are having this as the sugar. Okay, and suppose we are having this as the sugar. Now question can come, which of the following is reducing and which of the following is non-reducing. So if you look at the first structure, so basically this was the first carbon, this was the anomeric carbon, or this was the hemiacetal carbon of the monosaccharide. So basically it has now converted into OR. So this has basically converted into a acetal bond. Similarly, if you look in the second ring, so this was basically the initially anomeric carbon or the hemiacetal carbon. So this has also converted into OR and OR. So this has basically again converted into a acetal group. Now we know that acetals are stable and they do not hydrolyze, they hydrolyze only in acidic medium. So this won't hydrolyze and this won't give us the free aldehydic. So they are non-reducing. They will not give Tollens agent test. But you will look at this structure. Now this is your OR, okay, and this is your OR. So this becomes your acetal carbon. Now if you look at this carbon, okay, this is having OH and OR. So this is basically hemiacetal group. Now this has one acetal and one hemiacetal group. Okay, now because it has a hemiacetal group, it will hydrolyze in solution, the ring will open and we will get a free aldehydic which will give the Tollens agent test. So this is basically reducing. So whenever we say, whenever we are joining two monosaccharides through their hemiacetal linkage, okay, we had joined these two monosaccharides through their hemiacetal linkage, so we will say that they are always non-reducing. And whenever we are joining from 1,4 position, okay, that is hemiacetal of 1 and the other linkage is formed from any other carbon except hemiacetal, then it will be a reducing sugar. Okay, so again a very important question comes in this topic as well. So let us look at some examples of disaccharides. So this is the structure of sucrose. Now sucrose on hydrolyzing, okay, now when we hydrolyze, okay, so basically when you hydrolyze a sucrose, so we'll get, just we'll hydrolyze like this. So when we hydrolyze a disaccharide, we'll get two monosaccharide. So we'll get OH over here and we'll get OH over here. So basically we are getting, okay, this. You have to remember these structures, okay, and you can remember this in a very efficient manner. This does not require a plain memorization, there is concept involved. Now if you hydrolyze this, we'll get this. Now we can clearly see that there is a fructose, there is a 5-membered ring and there is a 6-membered ring present, okay. So basically on hydrolyzing it is giving a okay, so basically on hydrolyzing this is giving this. So now just look at these structures. If you look at this structure, this is the hemiacetal carbon, okay, so this would be the first carbon of the glucose. So the OH is in a, say, inside the plane and CH2H will be outside the plane. So they are opposite to each other. So this is basically a alpha D glucose. Okay, so this is basically alpha D glucose, and if you look at this structure, okay, so if you are looking at this structure, so this is your hemiacetal carbon, OH and OR attached to the same carbon. So if you look at the OH and the CH2OH, okay, so OH and the CH2OH, they are in the same plane. So this is basically beta D fructose. Okay, so basically a sucrose on hydrolysis give alpha D glucose and a beta D fructose. Now alpha D glucose has a rotation of plus 52.7 degree, and this is something around minus 90 degree. Okay, so basically the mixture is, this is rotating 52 plus 52, this is rotating minus 90. So basically the net rotation would be minus only. So the mixture would be behaving as a levorotatory, and sucrose is having plus rotation. Okay, so when you hydrolyze sucrose, which was rotating the light in the clockwise manner, now the mixture that formed would rotate the light, plane polarized light, in the anti-clockwise manner. So we say that there is an inversion of configuration. That's why the mixture of these are also called as invert sugar. Okay. So if you look at the structure now, so I can say that because this is the, okay, so this is the hemiacetal carbon of glucose ring. So this is basically glucose, and this is basically the fructose ring. So this is the hemiacetal carbon of the glucose. So basically if you look at this bond, this and this is opposite. So this is basically a alpha bond. So I can say this is a alpha glucosidic linkage. Okay, I can say this is a alpha glucosidic linkage. Similarly, if you look at the fructose, so this is basically O and O. So basically this was your hemiacetal carbon. Now the OH and the CH2OH, like we have done in the hydrolysis structure also, they are in the same plane. So basically this is the beta bond. Okay, so we'll say this is a beta fructosidic linkage. Okay, I hope this is clear to everyone. So this is having basically alpha glucosidic and beta fructosidic. So basically this is having a glycosidic linkage between, so this was your first carbon, second, third, fourth, fifth and sixth. So this is having one first carbon of the glucose and the second carbon. So basically it is having C1, C2 type of glycosidic linkage. Okay. Now will this be reducing or non-reducing? This is a non-reducing sugar, because both the individually, if you look at the structure, both the hemiacetal carbon combined together and formed the acetal. So this become acetal OR, OR. This carbon also formed OR and OR. So both of them become acetal. It cannot open up in acid in the medium, and it cannot form a free aldehyde. So basically this is a non-reducing sugar. So again a very good example. So basically sucrose is formed by the condensation of alpha D glucose and a beta D fructose from C1 carbon of glucose and C2 carbon of fructose. So basically both the hemiacetal carbon are condensing together and forming a acetal. Okay, so that's why we say this is a non-reducing sugar. Now let us look at maltose. Now if you hydrolyze maltose, maltose is also called as malt sugar. Okay, so basically if you hydrolyze this, so we have to just break, this is the acetal bond OR, OR. So this is the basically acetal bond O, carbon R, O, okay, R. So this is not your regular acetal bond. Okay, so this is the only acetal bond. Okay, I hope this is clear to everyone. Now if you look at this, this is the hemiacetal bond. Okay, OH, OR. So basically the two units are combining, one hemiacetal carbon and other carbon of the other molecule is combining, which is not hemiacetal. So if you hydrolyze this, just put a H over here, OH over here. So we will be getting this as the molecule. Okay, so we'll be getting this as the molecule. Now because this was a acetal carbon, that means it was formed from a hemiacetal carbon. So this bond is basically the OH and the CH2OH are opposite. So basically this is alpha bond, alpha with respect to glucose. So we'll say this is a alpha glucosidic linkage. So this was basically alpha glucosidic. So this has basically condensed from, okay, so this was your first, second, third, fourth, fifth, sixth. So C1 and C4 of two units have attached together. Okay, now this we cannot say that it is a glucosidic bond because basically the hemiacetal bond is over here. So we will say that this is joined through only a alpha glucosidic bond, and hydrolysis it is giving alpha D glucose. Okay, so maltose is just made up of 2 moles of alpha D glucose. We just condense it from C1 and C4 position and we get a maltose structure. Now again a question can come, whether this is a reducing or a non-reducing sugar. Now if you look at the structure, this carbon has from a hemiacetal, it has converted into a acetal carbon. So this becomes non-reducing. But if you look at the another ring, okay, you have to keep looking for all the ring. So in this, this is basically a hemiacetal carbon. So this will open up, hemiacetal are unstable, it will open up and form a aldehyde, and this will give the test of aldehyde. Okay, so this is basically overall a reducing sugar. Now if you look at the structure of lactose, okay, so basically lactose is made up of beta D galactose and beta D glucose. Okay, remember glucose C2 epimer was mannose, C3 epimer was allose, C4 epimer was galactose. So if you draw the structure of beta D glucose is basically the OH at the hemiacetal carbon and the 6th OH are in the same plane. So just remember how I told you, just forget this, second OH on the going down, third OH right going above, fourth OH coming down, fifth or the 6th OH on the opposite plane. Okay. Now because this is the beta D form, so the first OH and the 6th OH will be in the same plane. So you can write this structure. Similarly for writing the galactose structure, so the configuration of first 2, 3, 4, 5, 6, the configuration at all the carbon remains same, only it will change at the 4th position. So the 4th position was OH was going down, so it will go in the upper plane because it is epimer. So this is a beta D galactose. Now you combine it from a very important point. In this case, this was the beta galactosidic linkage. Okay, because this was the beta, okay, the hemiacetal carbon of galactose, the OH was outside the plane. So this is not a carbon, this is just pointing that this is outside the plane. Okay, this is in the plane with 6th carbon. So basically this is your beta galactosidic, and if you look at this we cannot classify at a alpha or a beta bond because the hemiacetal carbon is present over here. Now this is your beta, okay, OH and the CH2OH are in the same plane. So we will say that this is having only a beta galactosidic linkage, and this is not having, will not do a nomenclature of the bond with respect to glucose because the glucose hemiacetal carbon is free over there. Okay, so we will say that this is also a reducing sugar because when you take it in tolerance reagent, so this will not open up because this is a acetal bond, but because there is a hemiacetal linkage present over there, it will open up to give a free aldehyde which will give the test of tolerance reagent. Okay, so in this we will say that there is a C1 C4 linkage between the 2 units. Okay, so lactose is also basically a milk sugar. Okay, so I hope these structures are clear. You need to remember sucrose is made up of alpha D glucose and beta D fructose. It is a non-reducing sugar, meaning that both the hemiacetal carbon have combined and changed into acetal. So it is having alpha glucosidic linkage and a beta fructosidic linkage. Similarly, if you look at maltose, because it is a reducing sugar, it means that the linkage between C1 and C4. So it basically on hydrolysis give 2 moles of alpha D glucose. Similarly for galactose, it is made up of beta D galactose and a beta D glucose. Okay, so let's quickly go into polysaccharides. Basically polysaccharides, first case is the starch. Starch is the main storage polysaccharide of plants. It is the most important dietary source for human beings. High content of starch is found in cereal, roots, tubers and some vegetable. It is a polymer of alpha glucose and consists of 2 components. So basically starch has 2 components, amylose and amylopectin. Amylose is basically water soluble and constitute 15 to 20% of starch. Amylopectin is water insoluble and it constitutes 85 to 80% of starch. So if you look at the structure of, now all polysaccharides are basically non-reducing. So you should know that polysaccharides are non-reducing. In disaccharides only sucrose is non-reducing, else all other are reducing in nature. Okay. So if you look at the structure of starch, starch is basically the polymeric form of alpha D glucose. So it can be called as a natural polymer also. So alpha D glucose are condensing together. Okay, so for condensation what will happen? Hemiacetal of one carbon, the fourth carbon of the other, hemiacetal of one, fourth carbon of other, hemiacetal carbon of one, fourth carbon of other. So they will combine together and they will form a sucrose, or they will form a starch. Now this is the basic structure of amylose. So in amylose there is a linear chain between the alpha D glucose. So just you have to do the hemiacetal carbon of alpha D glucose combines with fourth carbon of the other glucose, then the hemiacetal of that glucose combines with fourth of other, and so this link will go on. So this is basically, starch is basically a linear polymer of alpha D glucose. Amylopectin basically has branching at the sixth position. So amylopectin has also a linear chain and they will be branching at the sixth carbon. Okay, so you have to remember this. Now the next important is cellulose. Now cellulose occurs exclusively in plants and it is the most abundant organic substance in plant kingdom. So basically if you look at the plant cells, they are made up of glucose, they are made up of cellulose. Okay, so basically it is again consisting of beta D glucose which are joined by glycosidic linkage. So basically starch is made up of alpha D glucose and cellulose, which is an important constituent of the plant cell, is made up of beta D glucose. Okay, so beta D glucose will combine again C1 of one, C4 of the other, C1 of one, C4 of the other, and then they will keep on growing. So will form a cellulose. Okay, so just need to remember these structures. Okay, glycogen. Okay, the glycogen is basically the carbohydrate that are stored in animal body. It is known as animal starch because its structure is similar to amylopectin. So basically glycogen is structure is similar to amylopectin. Now amylopectin was a polymer of alpha D glucose. So this is again a polymer of alpha D glucose, but in this case there is a lot of branching. It is present in liver, muscles, brain. When body needs, the enzyme breaks the glycogen into glucose and we get the energy. Okay, so these are basically all the monosaccharides and disaccharides and polysaccharide structure. So just go through the lecture once again, have a very important conclusion about the reducing, non-reducing sugar, the structure aspects of disaccharides and polysaccharides. You should know the structures of all the polysaccharides and the disaccharides that are there in the NCERT reaction of glucose. So in tomorrow's lecture we will do some test. We are basically like we have not covered 2 or 3 very important points, that is test of carbohydrates. We will cover in the next lecture and we will start with amino acids and protein. Okay, so I hope it being a theoretical lecture, I know it might have been a lot of theory today, so it might have little boring, but just stick with us, just read this portion because this is actually very important. A definite question is awaiting in JEE Mains as well as advanced. Okay, so we will catch tomorrow for some more interesting sessions on proteins and amino acids.